Good evening, everybody. Hi, welcome to watching PLG mid-semester exam revision for QBUS5001. This is Tony speaking. So as I said yesterday, our mid-semester exam mainly contains three parts. The first part is about descriptive statistics or descriptive measures, especially the numerical descriptive measures. And secondly, we mainly talk about the probability theory. Oh gosh, sorry, I'm too hungry. Probability theory, as well as random variables and probability distribution. So this is the second thing. And the third thing is central limit theorem. So yesterday, we basically finished the descriptive measures. We also finished a part of probability theory. So what we'll be focusing on today is the random variables and probability distribution. Okay, random variables and probability distribution. And if we got enough time, we can cover a little bit about central limit theorem. Okay, so random variable, probability distribution. Hopefully you are ready with random variables and probability distributions. Okay, now from yesterday, hopefully you still remember we talked about four basic concepts. Those are random experiment, so we have random experiment whose results are random. And the random experiment will generate outcomes. So outcomes, and all outcomes, putting them all together, O1, O2, O something, and putting them all together is called sample space. And lastly, any subset of those outcomes are called events. Therefore, when we talk about probability, we basically talk about the features of events or outcomes. So from yesterday, we get to know that the probability is actually describing a feature or the likelihood of any event to happen. Okay, so probability describes features of events. Now, today we are going to have a new definition, which is called random variable. Okay, random variable. So what is a random variable? Well, first of all, a random variable is usually denoted by capital letters, okay? Capital letters. For example, big X, okay? So a random variable is defined to be a function of outcomes. So when we talk about function, oh, someone is asking question. I'll answer your question later on, okay? So what I'm talking about, X equal, oh, okay. So random variable is the function of different outcomes. So when we talk about function, it means whenever there's an outcome, X correspondingly will have a value to that outcome. So for example, if we still considering rolling a die, okay, so 1, 2, 3, 4, 5, 6, so six possible outcomes. So this X can be defined as 1 when 1 is facing on top, okay? When 1 is on top. So this is an event or outcome, and when 1 is on top, the x will equal to 1. And 2 is on top equal 2. 3 is on top equal 3, 4, 5, 6. So that we try and convert this random experiment with some outcomes into a variable that can be directly explained in numbers, okay? So probably this is not a very obvious example, but one more example can be if you flip a coin, you have head and tails, right? So you can also define another random variable y, and y equal 1 when there's head, and when y equals 0 when there's a tail. So that you can say you try and convert those categorical values into numerical values, so that later on we can basically doing some calculations on the random variables. So that's why we bother defining random variables to stand for the different outcomes from a random experiment. Okay, so that's all about random variables. Okay, random variables. So whenever we talk about random variables, there are two different types of random variables, and as I said, our week 3 is mainly talking about different random variables. So we have discrete random variables whose values are discrete numbers. And we also have continuous random variables. Continuous random variables. So for example, the waiting time, right? So let's take some examples. A continuous random variable can be waiting time of a bus, right? So the waiting time can be 1 second, can be 1.00001 second, or 0.9999999 seconds. So it can basically take any value to represent waiting time. But for discrete ones, it can be the result of flipping a coin or rolling a die, right? The result of rolling a die, so that they are discrete values, okay? All right, so discrete random variables and continuous random variables, and again, for each random variable, there is also a probability feature corresponding to any random variable, and that feature is called probability distribution, okay? Probability distribution. So that how do we understand random variable and probability distribution? Let's go back and see probability and events, okay? So you may probably notice the probability describe the feature of events, so that in any problems, you will define the events first and then figure out their probabilities. Now, a random variable can be regarded as different events, right? Putting them all together from one random experiment, right? So for each result or each outcome, or we can say, or for each event here, there will be one probability corresponding to each outcome, right? So probability distribution is actually a measurement of probability on each one possible outcomes of this random variable. So for example, when we talk about probability distribution, it can be written in a table form. So for example, if I have this kind of table, and x value can be 1, 2, 3, 4, 5, 6 for this rolling die experiment, right? And then here you have to pay attention. The probability the notation here is the probability of the big X, which stands for the random variable, equal to small x. Small x is the possible outcome of this random variable. So here it's probability of big X equals small x. So this is the right way of denoting a probability corresponding to random variable equal to a particular value. So, for example, if the outcome is 1, the probability is 1 over 6, 1 over 6, 1 over 6, 1 over 6. So each outcome result will be 1 over 6. And this is pretty straightforward. And this table is called a probability distribution. So it basically describes how the probabilities or possibilities are distributed among different possible outcomes of any random variable. Okay, so yeah, that's all about probability distribution. And again, when we talk about probability distribution, since there are discrete random variables and continuous random variables, there must be some discrete distribution and continuous distributions, and that's all you learned from week 3, right? But before we move on to introduce any particular distribution, one last thing you have to know is the calculation of the expected value and the variance of any random variables. So EX, for example, is for discrete random variables, it's simply the probability of any of the numbers multiplied by the X values. So the XI values, it's the sum of them. So basically, if you want to calculate on average what is the outcome of rolling a die, then all you're going to do is to 1 multiply by 1 over 6, 2 multiplied by 1 over 6, 3 times this, 4 times this, and add them all together. So it's the sum of the product of probability and the outcome of the random variable, or the value of the random variable. So this one is pretty straightforward. And for the variance, similarly, it's the probability multiply any xi minus ex to the power of 2, or the square, right? So this is one way of calculating the variance of any random variables. So this is something that you also need to know. But anyway, you will be given the formulas, and very likely you will be given this kind of formula. So you'll be given sometimes ex squared minus ex squared. So this is an alternative way of calculating the variance of a random variable. And yeah, as I said, all those formulas will be given in your formula sheet. And one last thing I want to mention regarding the expected value and the variance of random variables is some rules. And that the application of those rules, it's from the one application is called portfolio diversification. So basically, that rule states that AX plus B equal what? Equal AEX plus B, right? So this is one thing. And another thing, variance AX plus B equal A squared VX, and don't plus B, right? Because you add or minus something will never affect the volatility of that data. So here are the first 2 rules that you need to keep in mind. And we also learned about X and Y. If we have 2 random variables, X and Y, so the expected value of AX plus BY, it will just be equal to A times EX plus B times EY. So as I said, this is the formula for portfolio return, right? portfolio average return. So in the portfolio return formula, A and B are just the weight on each stock return, and EX and EY are just expected returns on two different stocks. And also for variance AX plus BY, it equals A squared variance X plus B squared variance of Y, and multiply by plus 2AB and covariance of X and Y. Okay, and also this covariance can also be written in rho XY, which is the coefficient of correlation, and then standard deviation of X, standard deviation of Y. Okay, so here are the two versions of portfolio returns and portfolio standard deviation or portfolio variances. And as I said, in order for the variance to be smaller than each of the variance of that, we have to require rho to be less than 0, okay? But anyway, in terms of portfolio theory or portfolio diversification, I think we do have a separate video introducing portfolio theory. So I'll only list the formula here. So I would like you to watch the videos, as I said in the ED announcement, right? So watch the video, portfolio diversification from our PLG official channel. Okay, all right, so that's all about the basic knowledge regarding random variables. So let's do a quick recap on it. So random variable is described by probability distributions. So one feature of random variable is probability distribution, and events correspondingly, they have probabilities. So when we put all the events together, we have a random variable, and then the probability of each of them is a probability distribution. Okay, something like that. All right, now before we move on to introducing discrete random variable and continuous random variable, let's see Emily Wong's question. Just want to clarify if event A have test, A bar is no test. Are these two events or one event? Well, they are two events. They are two mutually exclusive and exhaustive events. So they are two events, all right? Okay. Now, let's move on to introducing discrete random variables and continuous random variables, or discrete probability distributions and continuous probability distributions. Okay, so first, let's look at discrete random variables. So for discrete random variables, you basically learn two of them. The first one is the easiest one, that is called binomial distribution or binomial random variables, right? Binomial distribution or binomial random variables. Well, for binomial distribution, I will use binomial distribution as an example. When you do a revision, you should consider 5 aspects on each distribution. So once you know all the 5 aspects, you will have no problem in any kind of exam questions, okay? Now, let's start with binomial distribution. The first aspect you have to know is the story or assumption behind binomial distribution. So story, or you can call it assumptions behind binomial distribution, all right? So for binomial distribution, what is the story? So you first learned a Bernoulli experiment, right? Bernoulli experiment. So for Bernoulli experiment is a kind of experiment that has only two results, two mutually exclusive and exhaustive results, such as flipping a coin, right? So for Bernoulli experiment, there are two results, either success or fail, right? Success or failure. So this is called Bernoulli experiment. And we define the probability of a success to be P and failure will be 1 minus P because they are mutually exclusive and exhaustive events. Or we can use the example from Emily Wong, right? So she said event A is have test, B is no test. So test, no test is also a Bernoulli experiment. Those are two events from one experiment, okay? Now, for binomial distribution, once again, I just want you to know, all distributions is describing random variables, right? So in this kind of questions, you should always find out the random variable in the questions and then define its distribution. So later on, I will probably use an example from your previous semesters and to say what does that mean, okay? So for Bernoulli experiment, if we repeat, right? So the key word is to repeat this Bernoulli experiment for n times. All right, repeat the Bernoulli experiment for n times. Then the number of success, right? Because if we repeat for n times, there must be a number that is success and another number that is failed, right? So the number of success, we define it as x or random variable, and this random variable follows binomial distribution, okay? So we can say that the number of success follows binomial distribution. And if we define x to be number of success, because the number of success is a random number, right? Or random variable. So we can write as x follow bin for binomial. And binomial has two parameters. One is n and the other is p. Okay, so n stands for repeat the number of times repeating that Bernoulli experiment, and the p is the probability of success in that Bernoulli experiment. Okay, so that's the first aspect. Okay, the first aspect, aspect one, story or assumptions. And the second aspect I want to mention here is roughly you need to know how the binomial distribution look like on a graph. So you don't have to know it precisely, but the second thing, the shape of the distribution or the graph. The shape of the distribution for binomial is a number of bars, right? A number of bars. So the peak of the bar depends on the probability, right? It can be symmetric or not symmetric. And later on, you know, if n is large, np is greater than 5, n times 1 minus p is greater than 5, it can be approximated by a normal distribution, right? So you need to know it roughly like this. So that what's the point of knowing the graph? This will apply when you try and calculate some probabilities, right? So for example, this is n equal 10, for example, okay? And you're asked to calculate the probability of x greater than or equal to 9, okay? And what if in your exam, you try and calculate this result to be 0.97 something, okay? then you will definitely understand this result must be wrong, because 0.97 is this area, right? It can be that large. So you probably know, oh, I forgot to use 1 minus the probability of f less than or equal 8 to calculate that probability, right? So yeah. I mean, if you understand the graph, you can quickly identify if your result is correct or incorrect, okay? So the second thing you need to know is about the graph, the shape of the distribution. All right, 1, 2, 3. Okay, now the third aspect of any distribution is to know their probability mass function for discrete, right? So probability mass functions, well, or PMF. Well, for continuous ones, it's called PDF, right? So probability mass function is a function that defines the probability when x equal to any small x. So it's basically the distribution function, right? So using probability mass function, you are able to calculate the probability of any random variable equal to any particular value. For example, if the question asks you to calculate the probability of the number of success equals 6, right? And then you can plug in the number 6 and calculate the probability, right? So the probability mass function of binomial distribution is given by C and X. So here is a small x because this is the actual results, right? And this is the random variable, C and X. And you might have noticed it's upside down, but that's the Australian Y, okay? And probability of success to the power of success multiplied by the probability of failure to the power of the number of failure, n minus x. So this is how we calculate the probability of x equal x. And also you can calculate that using Excel with binom.dist, right? And the first one should be the number of success x, and second one number of trials, third one p, and the last one is whether cumulative or not. So if you calculate the PMF or the probability of x equals something, and you're gonna use the 0, right? So you're gonna use 0 or false for non-cumulative probabilities. So this is the third thing you have to know regarding any probability distribution. So third thing, probability mass function, PMF. Fourth thing, CDF, it's called cumulative distribution function, right? PDF. So, well, no, it's not PDF. It's called CDF. Sorry, CDF. It's called CDF. So, for discrete random variables, we understand that the probability of x less than or equal to any value will be very easy to calculate. It's simply the probability of x equals 0, x equal 1, plus x equal 2, till x equal x, right? So it's the sum of the probability of x equal I or xi or any value, and I from the very first value 0 to x, right? So yeah, this is how we calculate cumulative distribution function, and this function will apply for all discrete random variables. Okay, Ray C1 is asking, how can we calculate the x You mean I believe you're asking how can we calculate the probability of x, right? Probability of big X equals small x. If the x is a large number, such as x equal 1,000. So that is when we apply normal approximation of binomial probabilities. So if you want to know more about the normal approximation of binomial probability, go to YouTube and to search my this PLG channel. In episode 2, I guess, there is a normal approximation of binomial probability. So to answer your question, Ray Xiwen, we can use normal approximation. Okay. But anyway, let's continue. Cumulative distribution function, CDF. And in Excel, again, you can also calculate that kind of probabilities using binom dist. Again, x and p, but instead of 0, you have to input 1 over here because it should be this kind of bracket, right? Okay. This is how we calculate the cumulative probabilities. So in the question, if you're asked what is the probability of x or the probability of this number of success is less than 2, so you can calculate that. And one last thing, for all discrete distributions, if you are asked to calculate of x greater or equal to any x, then you understand you have to convert that into the 1 minus probability of x less than or equal to x minus 1, right? So that they include the same thing, basically. Okay, so you can also calculate this probability using Excel. Or by hand. So you repeat doing this, you plug in 0, 1, 2, 3, 4, 5, and then calculate all the probabilities. Anyway, this is how we calculate the cumulative distribution function. And lastly, for each distribution, we'll introduce 5 aspects, right? So lastly, the last aspect is the discrete measures, which are expected values, and variances. So expected value and variances of a binomial distribution. So as we know, you probably know if x follows a binomial NP, the expected value is just NP, and the variance is NP multiplied by 1 minus P. So this is how we find out NP and NP 1 minus P. Well, Yun Zhu is asking, do we just need to write the Excel formula as the result for this kind of question? It depends on how the question is asking you, okay? If the question didn't say anything, you have to calculate the result, okay? But if the question asks you, what is the Excel function to calculate that result, then you write down the Excel function, okay? So it's all about what you are asked in the exam, all right? So all of those are the 5 aspects of a binomial distribution. Story, assumption, graph, distribution, probability mass function, CDF, and expected value and variances. So for later on, for each of the distributions, I will focus on those 5 aspects to do the revision, okay? So everything, 5 aspects, all right? Okay, now, let's see if there is example question. Okay, what about we finish all the knowledge and then we look at one particular questions as an example to help you solve the problem, okay? And I will also, as I said yesterday, let's see how many viewers are now. Around 100 people is watching. So you're so lucky to watch this video because I'm going to later on introduce how to achieve full mark in answering questions. Okay, but before that, hopefully you already finished taking notes, okay? Because for any of the distribution, just memorize those 5 aspects, and you'll be very happy with all kinds of questions. Okay, all right. The second distribution is called the Poisson distribution. I mean the discrete ones. Poisson distribution. Distribution. Okay, Poisson distribution. Again, let's think about the 5 aspects. So the first aspects, again, story and assumptions. So for Poisson distribution, the story behind Poisson distribution is usually describe the number of occurrence within a certain interval. Okay, the number of occurrence in any interval. All right. So for example, no example here, but the number of occurrence. Okay, number of occurrence in a given example. So I believe if you finish your tutorial, you must be very familiar with those distributions in a given interval. So this number of occurrence in a given interval, this number follows is said to follow Poisson distribution. If, okay, so it's said this number, and let's define x to be this number of occurrence, okay? So x is said to be follow a Poisson distribution with an average occurrence of mu if, under some assumptions, right? If this occurrence is rare, right? Occurrence is rare, and those occurrences are independent to each other, right? With similar probabilities. Okay, so occurrence is rare and independent to each other. So in the questions, I believe in most of the questions, they will directly tell you this number of occurrence or whatever follows a Poisson distribution. So you don't really need to worry about to identify. But if you don't, if you are not given, then try and find out whether there's an interval and whether they give you the average. So mu is the average occurrence in that interval, right? Average occurrence, number of occurrence in that particular interval. So the typical story you may be able to memorize. Well, what do you mean by rare? Well, there is no definition of or no clear boundary of rare, but rare means they are not happen so frequently. Okay, it's not happening so frequently. All right. So for example, if you're sitting in front of a hotline desk, right? So the number of occurrence of the hotline or incoming calls can follow a Poisson distribution. All right. So probably you haven't learned this assumption, but that's why you will be given that something is following a Poisson distribution in the question. But it's still good to know them, right? Okay, so that's all about the story and the assumptions. So again, if you go to any questions, or what about we later on, we will cover a Poisson question, okay? And then we'll try and see how we solve that out. And secondly, the shape of Poisson distribution, or the graph of Poisson distribution. As the number of occurrence can be infinity, so it's a kind of bars, it's still a set of bars, but this bar can extend to theoretically, okay, positive infinity, but the probability will be very, very, very small, okay? But still, the range of x can be from 0 to infinity, all right? So this is the shape of Poisson distribution. Third thing, PMF, probability mass function. So PMF, as I said, it is used for a calculation of the probability of any random variable equal to a small value, a small x, right? X. And this PMF, I actually have a very interesting way of memorizing this PMF of Poisson distribution. Some of you might have heard of it, but let's look at it again, okay? So one day, it's a story. One day, X becomes very surprised, okay? X becomes surprised. So this is factorial, right? Why is that? That's because over the wall or over a window, he saw what? He saw mu is carrying his son. Okay, so X becomes surprised or angry, and mu is carrying his son, right? Therefore, X just said, and then killed mu, okay? So killed mu, all right? So X surprised because mu is carrying his son, and then killed mu. All right, so that's how we memorize the PMF for Poisson distribution, all right? This is the way we calculate the probability of, for example, the number of hotline equal 3, right? So if hotline equal 3, you will say 3 becomes very surprised because mu is carrying 3 and killed mu, right? Okay, so that's all about the PMF for Poisson distribution. And the fourth aspect, as I said, CDF, cumulative distribution function. And again, for any of the probabilities, I mean discrete probability distributions, X. The probability of x equal any small x is simply the sum of the probability of x from equal I, so I from 0 to x, right? So it's basically the x equals 0 plus x equal 2, x equal 3, probably x equal 4, to x equal like x, okay? So this is also very straightforward. And again, if you want to calculate x greater or equal to x, well, this is pretty simple. It's 1 minus probability of x less than or smaller than x minus 1. So same thing as binomial distribution, because both of them are discrete probability distributions, right? All right, so fourth one, CDF. Last but not the least, again, the discrete measures, right? Ex equal what? Mu. And the variance of x also equal mu. Beautiful. All right. Right. Okay. So Yang Lei is asking, how do we know from question that we should use Poisson distribution instead of binomial exponential? Well, we will be looking at the stories, right? So we should first code. What's wrong? Code. What do you mean by code? Anyway, so in the question, if you identify the right random variable, and you should first think about if it is continuous or discrete, right? If it is discrete, you'll be thinking about whether it's Poisson distribution or binomial distribution. And our Excel code, yeah, I forgot about that, but let me finish the question from Yang Lei, okay? And if you observe a number of occurrences in a given interval, like a given interval of time, like 3 days or 1 week, or interval of 5 pages, whatever, then this will be considered as Poisson distribution, or the question will tell you, okay? And for binomial distribution, you have to identify whether there are Bernoulli experiment, basically 2 outcome experiment, and whether there is repeating Bernoulli experiment, okay? So that's why you have to know the story and assumption of each distribution so that you are able to identify them from any questions, right? All right, so that's basically all about Poisson distribution. And as I said, I forgot to introduce the Excel code. So again, Excel code is POISSON, Poisson.dist. And the input should be x mu as well as 0. So here's 0. And for CDF, again, it's Poisson.dist and x mu 1, right? So similar things, all right? Okay, thanks for reminding me. Otherwise, I'll forget to introduce those Excel codes. Okay, so you can see in your notes, it will be very beautiful, right? Each distribution, 5 aspects. Okay, now the third distribution before we move on, the K distribution, or later on we still have uniform and normal distribution. They are not included in those 5 aspect notes, okay? They are so special. But the third one, I will introduce exponential distribution, and then we move on to the practice questions, okay? So thirdly, exponential distribution. For exponential distribution, it's discrete or continuous. Yes, it's continuous. Okay, so continuous distribution, exponential. Again, story. The story behind exponential distribution is that the waiting time. So exponential distribution is always describing the waiting time of the next occurrence, okay? So if we define x to be the waiting time of the next occurrence, and we also define 1 over lambda to be the average waiting time. Okay, waiting time of the next occurrence is x, and 1 over lambda is the average waiting time. So if that is the case, we can say x follows exponential distribution, exp for exponential distribution, lambda. So only one there's only one parameters in exponential distribution, average waiting time. So in the question, if you are given the average waiting time is 5 minutes, and then you have to remember lambda is 1 over 5 instead of 5, okay? So average waiting time is 1 over lambda. And yeah, that's why I say expected value is 1 over lambda, all right? So that's all about the story. And the shape of the exponential distribution looks like this, right? So the waiting time, through the waiting time, it's becoming less and less likely to happen, okay? So this is the shape of exponential distribution. And the third thing for exponential distribution is called the probability density function, because it's continuous random variable, right? So for continuous ones, we don't have probably a mass function. Why is that? Because we know that if we want to calculate x equal to a particular x, what is the probability? What's the probability of that? 0. Yes, it is 0. Because for continuous random variables, let's say if I say what's the probability of the waiting time to be 1 minute, exactly 1 minute. So what do you think? So it's very unlikely to happen to be exactly equal to 1 minute, right? So it can be 1.00001 or 0.099. So you can say it's very hard to reach 1 minute waiting time. That's why the probability of x equal x always equals 0. However, we do have something that describes the probability density of a random variable. of a continuous random variable. So when we talk about density, I'll explain it later on. But the PDF is usually called, it's usually denoted as fx or px or whatever. So fx is, oh, I suddenly forget. Anyone can tell me the PDF of exponential distribution, because there's no funny way to calculate that. But if I forget it, it means what? You don't need to know it, right? But there must be a PDF. Well, let me search on Wikipedia and see what's the PDF for exponential distribution. Okay, the PDF is lambda multiplied by e to the minus lambda x, okay? So this is called probability density function, okay? Now, one more thing, the fourth thing, right? Oh yeah, I forgot to say, well, if you do want to calculate the density, but basically it doesn't mean anything, well, I will not tell you the Excel formula, okay? So the fourth thing is the cumulative density function, CDF, cumulative distribution function. So the CDF for exponential distribution, which is usually denoted as, what? I don't know, but for example, another fx, big fx or whatever, it's up to you. Just tell the difference between the PDF and CDF, that's enough. So big fs, for example, it's equal to 1 minus e to the minus lambda x. So actually, this CDF, it's just the integration of a PDF, okay? So this shape is actually the shape of PDF. And you might have learned the area under this line stands for probability, right? So the area stands for probability. And each value here stands for probability density. So if you really want to understand that, you probably learned middle school physics before, right? So we know that velocity equal to what? Density multiplied by what? By mass, right? Velocity equal to density multiplied by mass. Mass is whatever. Density. Density is rho, right? Oh no. Mass is equal to rho multiplied velocity. Oh, m equal rho v. Oh my gosh, I can't remember. Okay, let's forget it. But if we think about mass as probability and rho as the probability density, and then the velocity will be how large the interval is, right? So if you multiply the velocity of that probability, and then you will get P. So that's why this area stands for mass or probability. And that's why we have probability mass function, because that's already the probabilities themselves. But here you have to multiply by velocity to get a mass. Okay, but it doesn't matter. If you don't know it, just ignore me, okay? I'm just trying to use physics to explain, to help you understand CDF and PDF. So for CDF, it's basically the probability up to any x value. So for CDF, it describes all the probabilities up to x, okay? And if you do want to calculate, for example, well, let's introduce the Excel code, right? The probability of x less than or equal to small x, well, this equal can exist or cannot. It doesn't matter if the equal sign is here or not, okay? So this can be calculated by plugging in x in that formula, okay? So it's 1 minus e to the minus lambda x. Or in Excel, you can use expon.dist with x lambda as well as 1. So if you input 1 here, it's the CDF themselves. If you put 0 here, you will not get 0 because the 0 stands for PDF. So there are still values over here, okay? So yeah, that's all about the calculations for exponential distribution. And again, if you want to calculate the probability of x less than or equal to the x1 to x2, and it's simply the probability of x less than or equal x2 minus the probability of x less than or equal x1. And this equal sign, you can put equal sign there or not, it doesn't matter, okay? Because the probability of equal something equals 0. All right, so those are the probability rules for calculating exponential probabilities. Now, CDF, lastly, the descriptive measures. Ex equal what? As I said, 1 over lambda. And the variance of x equal 1 over lambda square. So that's all about exponential distribution, the 5 aspects of exponential distribution. All right. Well, someone says, what does lambda usually mean? Well, the lambda means, lambda means, as I said, lambda means the inverse of the average waiting time, okay? So because the average waiting time, as I said, is 1 over lambda, so lambda itself is the inverse of average waiting time. Okay, so the inverse of average waiting time. Okay, Qi Jieding is saying, I'm not sure the exact difference between lambda and mu of Poisson distribution. Well, actually, lambda and mu are quite correlated. So because the average number occurrence, if you use that to divide by time, then the interval, it will be the average waiting time for each occurrence. So I think there's several pages on your lecture slides talking about the relationship between a exponential distribution and a Poisson distribution, but I don't have any example question here. Sorry about that, but you must get it. Is there any meaning if we put 0 PDF? Yeah, that means the density, the probability density when x equal x. So it will return you with this value, okay? So that's why it's not 0. It will return that value, which stands for the density, okay? Okay, now, Qi Jieding is asking, can we say they are the same if they are under the same interval? Well, from my memory, let's open a new small topic, exponential versus Poisson, okay? So let's see, for example, the average waiting time for exponential distribution is, for example, 2 minutes. So the lambda will equal 1 over 2, right? And for Poisson distribution, if we specify within 2 minutes, the average occurrence number, the number of occurrence is 1, then you can say for each 1 minute, no, not really. Yeah. Let's say within 2 minutes range, the average occurrence is 1, so that the mu in 2 minutes will be equal to 1. And the mu in 1 minute, yes, so the mu in 1 minute will be equal to 0.5, right? So yes, that's basically the relationship between lambda and mu, and lambda and mu are the same, okay? So for some questions, you can solve them either using exponential distribution or Poisson distribution when they are kept in the same unit of the time intervals, okay? So this means 2 minutes, right? So for waiting time is 2 minutes, so lambda equal 1 over 2. So this basically means for each 1 minute, it occurs half of the times, right? And for Poisson distribution, again, within a 2 minute range, occurrence 1, so within 1 minute range, right? For in each minute, the average occurrence will be 0.5. So this is basically the relationship between exponential and Poisson distribution. If you do want me to further explain the relationship using an example, I have to prepare it for probably tomorrow or any additional video if you really want to know it, okay? Because I don't have any examples by hand, all right? Sorry about that. But so far, we finished the 3K distributions and all the 5 aspects of them. For binomial distribution, Poisson distribution, as well as exponential distribution. So we are so good, right? Now, let's go to your sample past exam papers and see if there are any questions that we can apply those distributions. Oh, great. We've got it. Let's look at the Citibank first. Citibank Australia is one of the credit card issuers in Australia, and it uses a credit scorecard to determine whether or not a credit card application will be approved. So again, credit card approved or not, we try and identify what? Bernoulli experiment, right? This is a Bernoulli experiment because we have credit card being approved or credit card not have been approved. Now, according to an internal document of credit card department, 40% of the application have been rejected. Okay, so we got to know the rejected probability to be 40% and not reject probability to be 60%. Okay, now on a particular business day during promotion period, 400 applications. So what is the number of N? Is 400, right? We repeat this Bernoulli experiment for 400 times, so we can easily identify the distribution of this question, right? So again, for binomial distribution, if you know the story, we can do that, right? Okay, now find the probability that more than 250 applications are successful using Excel. So again, in your exam, this is from 2015. Actually, to tell the truth, this is the question from my semester. So 2015 semester 1, it was the time when I learned QBUS5001. And this is exactly the same exam paper I had 4 years ago. So, oh my God, it's been 4 years. Last year, I said to my students 3 years ago. The year before last year, I said to my student 2 years ago. Now it's already 4 years ago. Oh my God, time flies. Okay, but anyway, let's see. If you want to get full mark in this kind of questions, you should first define the random variables, as I said, right? Because you have to show the markers that you really understand the distribution, the probability distribution. It's focusing on random variables, okay? So when we finish today's live streaming, the only thing, if you forget everything, but you still need to remember, every time you have this kind of distribution question, you have to do what first? You have to define the random variable first, okay? So now let's identify what is the random variable. It says a successful, okay? So what about we define successful number to be x, okay? So let x equal to the number of successful applications within 400 applications. Okay, look at that. I forgot to spell it, so yeah. Number of successful applications within 400 applications. And then you should write down, therefore, x follows a binomial distribution with n equal 400, which is 400 applications. And you have to pay attention. Successful application means not rejected, right? So it's 0.6 instead of 0.4, right? And now we're going to find the probability of, so you have to also write down the probability correctly. More than 250 applications, so it should be X more than 250 applications. So that will be equal to the probability of X less than or equal to 250. And this can be calculated in Excel by, well, it's hard to calculate it by hand, right? So let's just do it in Excel. So 1 minus the probability, so it's binom, right? Binomial dot distribution with n, pay is 250, n is 400, and the pay is 0.6, and cumulative, yes, cumulative. So yeah, this is the whole calculating process of this kind of questions. Si Pang is asking, do we need to write down assumption for binomial distribution? No, you don't. If you're not asked, you don't need to write it down, okay? If you are asked, then write it down. All right? But those assumptions that I introduced to you is mainly helping you to identify which distribution they are, okay? So after reading this question, if you identify something, yes or no, right? 2 results, success or failure, and then repeat doing it for 400 times, then you will know you're going to use binomial distribution, okay? And for normal approximation to binomial probability, find the probability between 135 and 175 application inclusive are rejected. So I think in another video, I have a example question for normal approximation for binomial probabilities, but I know you don't have time to watch that, so I'll continue introducing this finishing this kind of question again and show you how you should illustrate your answer or present your answer. I still remember I did this question wrong because I didn't even understand inclusive in English at that time. So I don't know whether they include 135 and 175 in that question. So I was also very, very stupid, right? So will we be examining the approximation binomial using Poisson? I don't think so, because binomial and Poisson, well, they are roughly the same, but only if you are asked using Poisson to do a binomial whatever, and you just do it and try to find what is mu and that sort of stuff. NP is just mu, right? So yeah. Now, secondly, again, using normal approximation to binomial probabilities. So the condition for normal approximation for binomial probabilities is to test if NP greater than 5. So you have to write NP is what? NP is 400 multiplied by 60%. So it's 46240, which is definitely greater than 5. And n times 1 minus p, which is 400 multiplied by 40%, which is 160, is also greater than 5. So both of them are greater than 5. So that we can, therefore, we can let y, okay? We can let y to be a new random variable, which follows a normal distribution with mean NP. So NP is 240, and variance is NP times 1 minus P. So NP times 1 minus, oh my god, what is NP times 1 minus P? So 640.24, 0.24, 400, it's 96, okay, it's 96. So yeah, y follows, oh really? I rejected. Yes. Thank you very much, Yifei Liu. Okay. Yeah, it's rejected. So okay. So let's just swap them. Okay. Swap them. So the average number of rejection should be 160, right? So this is 1 minus p. So we have to define a new p, right? Okay. Right. Sorry, I didn't read the question very carefully. Now we should define. Let y be this, and before that we should also let x be the number of rejection, right? Rejection in the 400 applications. and then we know that x follows a binomial distribution of 400, and p is 0.4. So you'd better write this down right at the beginning, because this x will be different from this x, right? This x is the number of success, and this x is the number of failure. So you should first define the new x, define the new n, and define the new p, right? And then you can have a test of whether np greater than 5 or n minus p greater than 5. So in this way, let's say we let y follows normal distribution. Since this one is satisfied, so the probability of x less than or equal to 175 and greater than or equal to 135 can be approximated by the probability of y less than 175.5 greater than 134.5, right? And then you can do a so-called standardization of that normal probabilities. So it's going to be so here we have y minus 160 over 96, square root of 96, which is the standard deviation, less than 175.5 minus 160 divided by square root of 96. And then here is greater than 134.5 minus 160 divided by square root of 96, right? So in this way, you are able to work out the probability. So this is normal, standard normal z, right? So this will be z less than that number, greater than that number, and you can search the table for the result, okay? All right, so basically that's how you answer the second question for normal approximation of binomial probability. So Yuzhen Wang is asking, isn't the second condition should be np 1 minus p? No, it's not. It's np and then n 1 minus p, because np times 1 minus p is the variance, right? So should we distinguish those two brackets? Well, I don't really care, but you'd better use the round bracket first and then use that bracket. But it doesn't matter, okay? As long as you show precisely what they are, and then it should be fine. Turpin Tan is asking, what is the difference between sampling distribution of sample proportion P and normal approximation of binomial probability? So that's a very good question, Turpin Tan. Because I also find that difference. When we talk about sample proportion, then we don't have to make this correction, right? But if we use normal approximation to binomial probability, we have to do that kind of correction. That's also what I found. So I think the golden rule will be, if the question asks you to use normal approximation to approximate binomial probability, then you use this correction figure. Otherwise, deal with it using the sampling distribution of sample proportion, okay? So if you don't understand what am I talking about, I mean for others other than Turpin Tan, we will cover that tomorrow regarding the central limit theorem, the sampling distribution of P and the sampling distribution of X bar. Why the range of y changes? If you don't know why the range of y changes, please go to another video, episode 2, which is normal approximation of binomial probabilities, okay? Yeah. So yeah, if you don't understand what I'm doing here, it's the right time to go to our episode 2, normal approximation of binomial probabilities, okay? Later. All right, question 3, find the exact probability in 2 using Excel. I don't want to mention that. It's just using Excel to calculate the binomial probabilities. All right, so that's the example of binomial distribution. Now, let's look at B. Okay, so we will just finish all these questions and then we will call it a day. All right. So B is talking about the number of claims received by the claim department of online insurance company can be modeled by a Poisson distribution. Oh my God, it's already tell us the Poisson distribution, right? So the number of claims. So we may later on define it to be X, right? The number of claims with a mean of 6 claims per hour. So this will be the mu of the Poisson distribution. So this insurance company is doing business 24 hours a day, 7 days a week. Oh, they're so good, 24/7. So find the probability that no claim is received in a particular hour. All right, so now let's do this question together. So it says the number of claims received is X. So again, first thing first, let X to be the number of claims received by the claim department in an hour, right? So this is important, in 1 hour. So X be, you just copy this down, right? And then write it as to be 1 hour, right? X. Now, therefore, again, you can see, in order to get full mark, therefore, X follows what kind of distribution, right? So you can see, every time we have to identify the first thing, right? We have to identify the random variable first, because you need to show the markers. All those questions is talking about random variables. And we have random variable follow any distributions. And from previous experience, when I do the marking of the questions, I saw a lot of students writing, this question is Poisson distribution. So what does that mean? This question is Poisson distribution, and then X follow what. So it doesn't make sense, right? So even though that student is able to calculate everything correctly, but he or she basically didn't show the right understanding of the question. He only know how to calculate, but he doesn't know what he's doing, right? So again, X follows the number of claims in 1 hour. Therefore, X follows a binomial distribution, Poisson distribution with a mean mu 6. And so we're gonna find the probability of no claim is received. So X equal 0. Okay, X equals 0, and this can be calculated either using Excel, or we can try and use our formula, because Poisson formula is the funny one. Do you remember? So 0 becomes very surprised or angry, because over the wall he saw mu is 6. 6 is carrying his son, and so she and killed the 6. Yes. Okay. So let's see. The result will be 1. It's e to the power of minus 6, and you can soon use a calculator to calculate that. I don't know what's the result of that. Let's see. Minus 6. It's around. I can't. Sorry, I can't. This is too complex. Too many 2 point something together. And Yunzhu is asking, so we only use binomial distribution to normal distribution when the question asks us to do that, right? Yes, I suppose so. That's what I thought when I was doing exams, okay? Okay, no claim is received in a particular hour. Done. Next. Find the probability that this insurance company receives more than 60 claims in a particular 12-hour period. Okay, 12-hour period. So for Poisson distribution, oh, thank you very much. Some students calculated out the result 0.0025. I'll trust you. Okay. The probability receive more than 60 in 12-hour period. So can we still use the previous X in the first question? No, we can't, because this is a brand new random variable, because this stands for the number of currents in 12-hour period. Therefore, we have to let a new x or y or whatever you like, okay, to be the number of claims received by the claim department in a 12-hour period. Right, so do you know what I'm writing here, right? The number of claims received by the claim department in a 12-hour period. And therefore, x follows what? A Poisson distribution with 6 is for 1 hour, so 12 hour will be 72 claims on average. So this will follow a Poisson 72. And we're going to find the probability of x greater than 60, more than 60. It's not greater or equal to, right? Greater than 60. And this will be equal to the 1 minus the probability of x less than or equal to still 60, because this is greater. And you can use Excel to work it out, right? It's Poisson dot dist NP, so no, it's not NP, it's 60, average 72, and cumulative, right? Now, some of you is asking, do we need a conclusion for each question? If you have time, you'd better write one, right? So find the probability, and you can say so or therefore the probability of blah 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 is 0.025. Yeah, that will be better, okay? And again here, therefore the probability of blah 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 is blah blah blah, right? If you can calculate that out. And Jaden Wang is asking, can I just let xk to be blah, blah, blah in k hours? Definitely you can, because as long as you can make the markers understand what you're going to write or what you mean, and that's more than enough, okay? Oh, it's a little bit blurry. The internet speed is a bit slow now. I don't know why, but it's probably because the mobile phone is too hot. Okay. All right. Whatever. Let's look at the very last question before we call it a day. Okay. Now, C, 12 marks. Australian Zoo in Queensland is one of the tourist must-go attractions, so you have to go there sometimes. Okay. It's very good. Australian Zoo. As this zoo is so popular, there's always a queue outside the ticket office in the morning. The waiting time, oh my God, whenever you say waiting time, it has to be, or very likely to be an exponential question, right? All right, so the waiting time before getting served by a ticket officer can be modeled by an exponential distribution with lambda equal 0.5. So if lambda is equal 0.5, it means the average waiting time is 2 minutes, right? Okay, now, first question is that show the probability that a visitor has to wait for more than 3 minutes in a queue in a particular morning is 0.2231. Okay, now, in the first question, we can simply let our x to be the number of the waiting time, right? The waiting time before you get served in the morning, right? Waiting time before you get served in the morning. Therefore, x follows what? An exponential distribution with lambda 0.5. So if we're going to find the probability of more than 3 minutes, so the probability of x greater than 3 have to be equal to 1 minus the probability of x less than or equal 3 or less than 3. They are basically the same, okay? It doesn't matter if you put equal sign here or not, because it's continuous distribution, okay? Now, so the formula will be 1 minus e to the power of, I can't remember the formula. Let's see, where's exponential distribution? Oh, it's here. The this is the CDF, right? 1 minus e to the minus lambda x. So 1 minus e to the minus lambda is 1 minus 0.5, x is 3. So you can calculate that result. I can calculate very quickly. It's 0.2231 because it asks you to show to show this, right? Okay. Now, here is the interesting question. A visitor has been waiting in a queue for 2 minutes. Find the probability that she has to wait for another 2 or more minutes to get served by a ticket officer. So you can see a visitor has already been waiting in a queue for 2 minutes. What does that mean? That means what? A condition, right? So actually this question is about a conditional probability. So let's work that out. A visitor has been waiting in a queue for 2 minutes. So this means the probability that already 2 minutes, this means he must be waiting more than 2 minutes, right? And find the probability that she has to wait for another 2 or more minutes to get served by a ticket officer. So this probability is x greater than 2. And what we need to find is the probability of another 2 or more minutes, which means x greater than 4. So in total, greater than 4, given that he's already waited more than 2 minutes. Okay? So this is the exact question you have to answer. So for the conditional probability, it's calculated by the joint probability x greater than 2 divided by the marginal probability, the probability of x greater than 2, right? So the joint probability here is actually, we can say x greater than 2 will include x greater than 2. X greater than 4 will include x greater than 2. So this is basically x greater than 4 divided by the probability of x greater than 2. Okay? So this probability will be, okay, so greater than, it's 1 minus 1 minus, so the 1 minus will always disappear. So it's e to the power 0.5 multiplied by 4 divided by e to the minus 0.5 multiplied by 2. So the final result will be e to the power of minus 0.5 multiplied by 2. So it's actually e to the minus 1. So it's 1 over e. So if you can calculate that result, please do that, okay? So you can see this question is actually combine our exponential distribution with the conditional probabilities. And as I said, this was my mid-semester exam question 4 years ago, right? 4 years ago. So when I figured out this kind of conditional probability, I was so happy that I can work that out, because I believe not all students is able to find out this is a conditional probability. So I was so happy that I didn't see the last question at all and directly skip to question 4. So I lose 4 marks directly by being so happy in the exam. Okay, so I lose 4 marks. So don't learn from me. Okay, so keep calm every time, all the times. Okay, in your exams. So yeah, the result is 0.3679. Thank you very much. 0.3679. Okay. So now again. I thought I won't see this question again, but I have to redo it. And you can see I lose 4 marks here, and I forgot the inclusive somewhere else, and I didn't do very well, and I only get 89 on this paper. So if you do better than me, then you can definitely achieve much better results. Okay, Bai Wei Liao is asking, why not x equal 2 or x equal 4? Well, since this is a continuous probability distribution, the probability of equal something is always 0, right? So has been for 2 minutes. Well, it says has been waiting in a queue for 2 minutes. So this means he's already wait for 2 minutes, right? But time will keep flying. So this means within first 2 minutes, there's nothing happen, right? So this means the waiting time is greater than 2, all right? Okay, the third question. At the exit gate of the theme park, 60 visitors are selected at random. Find the probability that 15 or less of them have waited in a queue for more than 3 minutes in the morning. You might use Excel to calculate the exact probability. So, okay, for this question, what do you guys think? What distribution shall we use? Okay, yeah, I heard somebody is talking about binomial distribution. Okay, so that's why I asked you to know the story behind each distributions. Okay, so let's see. At the exit gate of the theme park, 60 visitors are selected at random. So this is pretty much like repeating what? Pretty much like repeating a Bernoulli experiment. But let's see if there is Bernoulli experiment, right? Wait in a queue for more than 3 minutes. Okay, wait in a queue for more than 3 minutes. So there are two types of persons. One is greater than 3 and less than 3, right? Okay, and it doesn't matter where we put the equal sign because it doesn't make sense. So, okay, greater than 3 and less than 3, these can be success and fail, right? And if we repeat interviewing 60 visitors, they are exactly what? Binomial distributions. So again, in this question, let X to be the number of visitors that have been waited in the queue for more than 3 minutes. Okay, the number of visitors in the queue for more than 3 minutes. And therefore X follows a binomial distribution with n equals 60 and the p equal what's the probability of waiting more than 3 minutes? It's over here 0.2231. 0.2231. Okay, and now we're gonna find 15 or less. So we're gonna find the probability of X less than or equal 15. Then if you're going to use Excel to solve this problem, it's going to be binom.dist with 15, 60, 0.2231, and 1. Okay, so this is how we calculate binomial distribution questions. Okay. So again, for the conclusion, you can write down, therefore, the probability of blah, blah, blah is, if you can work that out in Excel, that will be fine. But since in your exam, there's no Excel usage, so I suppose there won't be any large numbers like that. So you will be only given, for example, less than 2, right? So that you are able to calculate them by hand, or even less than 1. All right, or you only asked to write down the Excel formula. All right. So what do you mean by for the last question? Bin for the last question. Yeah? Yeah? Okay. So yes, you're right. Binomial distribution for the last question. All right. That's all about the practice questions of today. Again, Rollstone is saying whether we can make it to normal. Definitely we can. If it's np greater than 5 and n times 1 minus p also greater than 5, we can use normal approximation of binomial probabilities. However, for this to be happen, usually if you only use normal approximation if you are asked in the question using normal approximation of binomial probability. Okay. So Yun Drew is asking, does uniform distribution covered in our exam? Well, as I said, I don't know. Everything is possibly to be covered in your exam, But uniform distribution, well, for uniform distribution, I think it's more than enough if you are able to understand the petrol or the oil question in your lecture slides, okay? So I think in your slides in uniform distribution, you do have a example that is about the petrol, right, or gasoline or whatever, what liter, how many liters, and they are evenly distributed or uniformly distributed, and you asked to calculate the probability of between 2,000 to 3,000 or whatever. So just find out that problem, and that's all you need to know about uniform distribution. Okay. And lastly, in terms of normal distribution, it's again, you don't need to know all the 5 aspects, and we know normal distribution is bell-shaped, and you also need to know what is standardized, what is standard normal distribution, right? Normal variable. It's denoted in for z follows n0, 1, and for normal distribution, for any normal distribution, for example, x can be followed normal distribution with a mean mu and variance sigma square. So here are the only 2 parameters for normal distribution. And in terms of the formula, the PDF and CDF, forget them, okay? It's something square root 2 pi something e to the power of blah, blah, blah. It's too ugly. You don't need to know them at all, okay? Yeah, and so again, we will continue working on normal distribution tomorrow, because tomorrow we'll be doing that normal the central limit theorem. So we will further apply on normal distribution as well. Now it's time for Q&A. Bai Wei Liao, can we use PDF of exponential distribution to calculate equal fold? No, we can't, because for the PDF, what you returned is not the probability, it's the probability density. Okay, so fx is minus lambda e to the, well, I can't remember what is that. It's lambda to e to the minus lambda x. If you plug x number in here, it returns you with probability density, but not the probability. Okay. This will give you probability density. If you in order to calculate the probability, you still need to know the velocity, right? So again, for this question, since x is continuous random variable, so the probability of x equal to 2 will be equal 0. Okay. So it can conclude the same answer, just one whether we can do well. Probably it doesn't make sense, right? How can we tell it is binomial? Sampling proportion distribution should use. Thank you very much for your question, Giraso. Sampling distribution of sample proportion will be covered tomorrow, and hopefully tomorrow you will get a very clear idea regarding when to use binomial and when to use sampling proportion, sample proportion distributions. But so far, as I said several minutes ago, you basically, if you are asked to use normal approximation for binomial probabilities, do you really use normal approximation? Otherwise, use sample proportion. Okay. Emily Wong is asking, by the way, for previous, will we be tested variance about 3 or 4 shares portfolio too hard for calculation? Well, I personally don't think so, because I know it's too hard for calculation. Okay. But 3 is okay to calculate, right? But no, I think 2 is enough. I think there is one question regarding the normal the portfolio diversification in this one, right? Yeah, this question. So yeah, you can see only 2 investments, right? All right. Any other questions? if you don't have any other questions, we will just call it a day. And it's already 9:08, and we've been on streaming for 1 hour and 40 minutes. I believe most of you are feeling tired, especially me. I'm feeling very tired, okay? So, all right. So, if no other questions, and if there's no other questions, I will see you guys tomorrow at the same time, okay? 7:30 tomorrow. And we'll be covering the very last topic, which is central limit theorem, all right? About that, what is variance-covariance matrix? You don't need to know it, or I'll explain to you tomorrow, okay? Variance-covariance matrix, it's in finance, actually. It's very advanced. It's a matrix consists of the variance of each stock on the diagonal, and the covariance of each two stocks on other areas. So this is called the variance-covariance matrix. All right. I didn't see the portfolio formula in the exam formula sheet. Well, I think if there's no formulas in that sheet, you mean in the previous exam or not? Well, this is the portfolio diversification formula, right? Yes? Okay, it's here. Yeah, it's already tell you. And here, right? So this is portfolio diversification formula. But if you mean for the new uploaded ones, I haven't checked that yet, but I believe there are similar formulas like this. This is the portfolio diversification formula. And again, if you really want to say know more about portfolio diversification, and as well as the normal approximation of binomial probability, I will share with you the link. Okay. Let me copy the first one. This is normal approximation of binomial probabilities. Okay, so well, I'll put it in the description of the video, okay? Normal approximation of binomial probabilities. The link to here is here. And portfolio diversification. The link is over here. Don't worry, 1 second, and you will see that in the video description. Okay. Copy. Okay, done. So if you refresh the page, you might be able to see the description area with the two links of the videos. All right. Okay. You mean the optimal weight? The optimal weight will not be tested in your exam. Okay. All right, and that's all for today's live streaming. Thank you very much for watching. And finally, also thanks Candice for helping over there to control the quality of our live streaming. All right, Candice, you haven't seen Candice before because Candice is one of our previous PLG facilitators, but she's taking a half-year gap. Or defer in this semester, but she's still voluntarily helping PLG. So thank you very much, Candice. And that's all for today. Thank you, and see you tomorrow.